This week in Maths and Algorithms, let's talk about sequences and series. The objectives for this week are to understand the difference between sequence and series, as they are very much interlinked, the formula for the nth term of arithmetic and geometric progressions, so looking at the two most common types of sequences and how we are actually evaluate a given term later on in the sequence, arithmetic and geometric series, so basically adding up all the terms of AP or GP, and finally closing off with recurrence relations, so slightly different view at programming with recursion rather than iteration, and then a little bit of contrast between the two approaches there. So let's start by talking about the sequences. So a sequence, the main definition of it is that it's a succession of ordered set of numbers called terms that follow a given rule. So straight off you notice the similarities between sequences and functions. With functions we talked about a particular rule that enables us to manipulate input and get some output. With sequences we still apply some sort of rules, but we no longer are interested in input-output pairs that come out normally from the functions. What we do instead, we describe sequences with a notation like this: sequence A at position n, so nth term in a sequence A is, for example, 2n plus 1, and then n takes only natural numbers. So we're looking at the actual whole numbers which are positive, so that we are talking about tangible full positions or places within an array or within a list, and then calculating those for a particular rule. So using this rule, you would notice that A1, the very first term of that sequence, well, what we do, we just replace n with 1, just like we would do with functions, and we find that the result is 3. If you try A2, you will notice that actually the next term in the sequence is 5. If you try A3, you will quickly notice that actually this is 7, and so on. So this generates a sequence which is 3, 5, 7. If we continue, if we are allowed to continue, and if we wanted to carry on iteration further on, then we would probably have 9, 11, 13, etc. until a point when we stop iterating, or when we cannot iterate any further. Now, sequences, they have many different applications. Mainly they are used to approximate functions, but also in signal processing and picture processing as well. Everything can be broken down into sequences and then tackled separately. For example, in music, you can think about the music signal or your favorite song even to be broken down into sequence of different sort of terms, playing one close to another. What you can do, you can then bring them down and increase, for example, bass and lower down treble, etc. So many different things you can break down into sequences in that sense. Obviously, we are not going to go into applications. Here in this module, we are focused on the pure understanding of mathematical objects such as sequences. The applications will probably come in year 2 or year 3 of your degree. So I hope you're looking forward to that. Now, let's have an example, very easy one, with a particular sequence. So a sequence is described with a over n, so sorry, the nth term, which is 2n squared minus 6n, and we are bounded with condition that n must be less than 10. Find the first 3 terms and the last 2 terms or elements. So first of all, the first 3 terms are a1, a2, and a3. N iterates up to the value of 10, but it doesn't reach 10, okay? It's not less than or equal to 10, meaning that the very last term will be a9, and the one beforehand must be a8. Okay, so these will be the 5 terms I need to find according to the question. So if n is 1, this n took a value of 1, then I replace n with 1 here. Sorry, that was minus 6 times 1. So overall we have 2 minus 6, that's minus 4. Then n takes a value of 2, so I replace n with 2 in both places, giving me 4 times 2, 8, minus 12, that's minus 4. 2 multiplied with 3 squared minus 6 multiplied with 3, well, that is 9 times 2, that's 18, minus 18, that's a 0. So my sequence starts with minus 4, 0. Then I don't know what it does, but it will terminate with A8 and 9, sorry. So taking the value of 8 now, squared minus 6 times 8, what we are going to have, we have 64 times 2, that's 128. Let's just note it down so I don't mess it up. Minus 6 times 40 is 8, which is 48. That's an 80. Okay, so I will have 80 here towards the end, the penultimate term in the sequence, and A9 is 2 multiplied with 9 squared minus 6 times 9. That gives me 81 times 2, 162, minus 54, so I believe that's 108, so I finish at 108. Okay, so this is how we can evaluate particular terms in a sequence based on its nth term formula or nth term rule that we have been given in the sequence. Majority of the sequences will fall into two brackets, arithmetic or geometric progressions. But before we talk about any of those, let's just basically touch upon the topic of limit of infinite sequence. So sequences and functions go hand to hand, as we already mentioned there. So it's only natural to talk about their limits. What happens in the long term if we keep increasing the terms? So let's consider a sequence an equal to 1 over n. What is happening to this sequence? If we start plugging in the values, a1 is equal to 1 over 1, and that's simply 1. But a2 is 1 over 2, which is a half. Then a3 will have a value 1 over 3, and that's 0.33. If you plug in 100, then you have 1 over 100, and that's 0.01. So what is happening as we increase n, as n gets bigger and bigger, this particular sequence is going to 0. It clearly decreases and it gets smaller and smaller. You can start plugging high numbers to convince yourself if you want to. So what we say is that as n tends to infinity, the sequence goes to 0. So we use familiar notation that we used for functions that limit as n goes to infinity, as n increases and increases, the limit of that sequence is 0. It never actually, no term is actually equal to 0, but we get infinitely closer and closer to it. So that means we are able to write a statement like this. So if it goes to a particular value, then we say we have a convergent sequence. So it settles down at some sort of a value. Otherwise, if it goes to positive or negative infinity, or if, for example, we cannot say if it settles down to either positive or negative infinity or where it goes, then we say it's a divergent sequence. So convergent and divergent are the types of sequences we can talk about. Convergent if it settles down to a particular value, divergent if it just blows off into minus or positive infinity. Let's just talk about arithmetic sequences next. So this is one of the main types of sequences and probably the easiest one to start from. This is a type of sequence such that there is a common difference between any two consecutive elements. So we can have an arithmetic sequence like 2, 4, 6, 8, 10, etc. Meaning that I keep adding 2, so I have a common difference 2 inside of the sequence. I might start with pi, for example, and then have 2 pi. Sorry, that's one term, of course. 3 pi, 4 pi, etc. In which case my common difference is pi. But the bottom line is that I always add the same number. A sequence like 1, 2, 5, then 7, then 10. This is not AP, this is not arithmetic progression, because here my difference is 1, but here my difference is 3, and it doesn't even matter that here the difference is 2. Already I'm adding something different to previous term, so this breaks down the definition of AP. So for AP you need to have the common difference, the same number added to every single term. So what's the formula for the nth term of this sequence? So let's have a look at generalizing the rule for this particular sequence. And therefore, by doing that, we will be able to derive a generic formula for any arithmetic progression. So here, 15, 11, 7, 3, and minus 1. The question is, what is happening here? So to go from 15 to 11, I need to subtract 4. To go from 11 to 7, I'm subtracting 4. From 7 to 3, I'm subtracting 4, and no surprise, from 3 to minus 1, I subtract 4. So indeed, this is, I just verified, by the way, this is arithmetic progression, because I have common difference to be always the same. And what else I know? I know that the first term of the sequence is 15. Okay, so first term of the sequence is 15. The common difference, d, could be written as negative 4. What is happening, and what I need you to realize what is happening, okay, for A2 is that we have 11, but 11 really is A1, this 15, plus negative 4. So I'm adding one common difference to what to get my second term. For A3, the A3 is 7, but 7 is 11 plus negative 4, but actually 11 is 15 plus minus 4 plus negative 4. So actually, to get third term, I still have the first term plus 2 common differences. And one last thing that I want to write down is A4, which is, as you can see, 3 from that sequence, and therefore this is 7 plus negative 4, and it can also be written as 11 plus negative 4 plus negative 4, or 15 plus negative 4 plus negative 4 plus negative 4. So to get A4, I need to add 3 common differences to the first term. Therefore, we end up with a generic rule for any arithmetic progression. If you want to find a specific nth term, then you need to look at the first term in the sequence, where you started from, and then you add 1 less than the number of the position you are focusing on times the difference. So here we had, in fact, A1, the first term, plus n minus 1 times the difference, didn't we? But n in this case was 2, so we had 2 minus 1, which is just 1, and therefore that confirms I had A1 of the value 15 plus 1 common difference of minus 4. Here we had A1, which is the 15, plus n minus 1, n is 3, 3 minus 1 is 2 common differences, 2 times minus 4, which is again confirmed by what we got in the original sequence. So this is the sort of the formula that you need to keep in mind. And even if you forget how the formula looks like, from arithmetic progression you are expected to sort of understand that this is what we are doing. We are adding 1 less than the number of differences to the first term. But to solve that particular problem, I want to know the specific formula for nth term of this sequence. So for an, what I do, I simply substitute my value of a1, which is 15, then I will have plus n minus 1 multiplied with the difference minus 4. I can then expand this, okay, bringing minus 4 into the bracket by multiplying it with any term inside of the bracket to get an is equal to 15 plus minus 4 times n will be minus 4n. Minus 1 times minus 4 is plus 4. The numbers can be added together because they are like terms, and therefore we end up with an is equal to 19 minus 4n. This is specific formula for the nth term of this sequence. Okay, and that's how we solve it. Then we can iterate much easier to find out, for example, what is 100. I would simply do 19 minus 4 times 100, and therefore find out that this is 19 minus 400, and that's negative 381, and so on. Slightly different problem. This time we are given a finite sequence. Okay, I didn't really mention that yet, but sequences can be finite or infinite, and the basic description and definition follows that of a function or a set. So it's finite if it terminates at some particular term, and it's infinite if it just goes on and terms are added forever. We never keep adding new terms. Here we have a finite arithmetic sequence. We know what is the first term. We can work out what is the common difference, and then we just need to apply this formula we just derived on the previous slide to find out how many terms, how many iterations need to be performed until I reach 95. So based on this sequence that I've been given, a1 is negative 13. That's where I start from. Common difference, to work it out, by the way, to know what has been added here, in case you are wondering how I work out these things, you basically take any term apart from the first one, any term, and then take away the previous term. So taking away minus 13 from negative 4, you will have minus 4 plus 13, and that's 9. Similarly, you can confirm that the difference is common by taking the next number, which is 5, take away previous, which is minus 4, and this confirms that yes, it is a 9, and this is a common difference. We keep adding 9 in this sequence. So now use the formula. an is a1 plus n minus 1 d. I want to find out what is n. So I want to find out what is this position, effectively. I know it's a finite sequence which terminates at 95. The question is how many terms, how many iterations I need to do before I reach 95. So 95 is the value of an, okay? So I know an is 95, so I can plug it into the left side of the formula, equal to a1, which is negative 13, plus n minus 1. N is the value I'm trying to find, so I don't substitute anything into it. That's the position I'm looking for. Multiplied with d, which is 9. So multiplied with 9. So now if I just expand the bracket here, I will have 95 equal to negative 13 plus 9 times n, so 9n, minus 1 times 9 rather, so that's minus 9. Altogether 95 equal to, combine the numbers together, minus 22 plus 9n. Bring this negative 22 to the other side, you will have 117 is equal to 9n, and then divide by 9 on both sides to find that n is equal to, let's see, I think that's equal to 13. 90 plus 27, yes, 117. So yes, n is 13, meaning that I have 13 terms. 13 times I need to go through my for loop, if you want to think about it this way, until I reach number 95 if I started with negative 13 and if my difference was 9. So here in this video I will bring in a little bit of Java implementation. I don't want to spend too much time on it. There will be more time spent on it probably during your lecture, but here to implement finite arithmetic sequence, all you need is one single for loop. So for n starting at -1, for example here, n goes up to 25, n goes in the increments of 6. So in this place, usually you would have n plus plus, which means you increase n by 1 every time you loop it. Here we are actually not increasing by 1, we are increasing by 6, and then we are printing all the n values that we have. So what would be the output of this simplistic function here, or simplistic loop? Well, we start with n equal to -1, so -1 will be the first value of n which is printed. Then we loop it again. This time n is equal to the previous value of n, which is -1 plus 6, that's a 5, so the next printed value is a 5. And we go on again, new n is equal to 5 plus 6, which is 11. Then we go again, 11 plus 6 is 17. We go one more time, 17 plus 6 is 23, so it's still printed, but then afterwards we come back to that for statement. 23 plus 6 is 29. We have been bounded by the condition that n must be less than 25, therefore I'm not printing and I'm not executing anything inside of this for loop anymore. So I ended up with a finite arithmetic sequence with 5 terms, starting with -1, ending with 23, with common difference, as you can guess, 6. So that's how I implemented my arithmetic sequence. The next type of common sequences out there is geometric sequence. So this time, rather than having a common difference, we have a common ratio between any terms. So I might have 2, then 4, then 8, 16, 32, etc. In which case I have multiplied by 2, going from term to term. So I have common number with which I multiply. I might have something like -1, 3, then -9, 27. Sorry, that's 27, of course. Then -81, blah blah blah. Okay, in which case the common difference, sorry, the common ratio, okay, we are talking about a GP here, is multiplied with -3 all the time, multiplied with -3, and so on. So this is the sort of sequences we are talking about when we get any term by multiplying the previous term by a common ratio. Thus, to get the nth term of a geometric progression, we have this little formula. Because if I'm looking at this very simplistic sequence that I produced in here, a1 is 2, okay, which is 2 multiplied with ratio of 1 minus 1. So what I'm saying here is that I multiplied 2, the first term, with ratio to the power of 0, and as we should know, anything to the power of 0 is just 1, so I still have the first item. But a2 is 2 multiplied with ratio to the power of 2 minus 1, so that's ratio to the power of 1, so I just multiplied with ratio, which was 2, and I get 4. To get a3, I got first term 2 multiplied with ratio to the power of 3 minus 1, so ratio to the power of 2. Ratio was 2 to the power of 2, which is 4. 2 times 4 is 8, and so on. So I can use that sort of idea and find out any term. So I can look for I don't know, 8 for example. So that would be 2 multiplied with 2 to the power of 8 minus 1, and that's a 7. So you have 2 multiplied with I believe 128, and that's 256, and so on. So this is the formula. Again, we need to keep in mind and understand where it came from, really. So oh yeah, and R, pretty much already mentioned that by explaining this example that R is a common ratio and A is the initial value. So we can denote A1 by simply saying this is A. This is just to get rid of the indices. We could also do that, just use A, notation of A, in the previous formula we derived for arithmetic progressions. So AN for arithmetic progressions was A plus n minus 1 d. So here you are. Here are the two formulas I need you to remember and understand going forward. Let's have a look at an example of a geometric progression and a type of question that could come up. So let the first term of a GP be 150 and the common ratio to be 1/5. Write down the first 5 terms of this sequence. So I know my sequence starts with 150 and then it progresses in a way that I always multiply the previous term with 0.2, which is the decimal version of 1/5. Now, A1 is known. A2, what I can do, I can substitute all the values that I know into the formula. So remember the formula on the previous slide for geometric progression was AN is equal to A multiplied with R to the power of n minus 1. So I take this first value, the initial term in the sequence, and multiply it with ratio to the power of 1 less than the position. Position is 2, so 2 minus 1 is to the power of 1, and that means I have 30. Okay, so multiplying these two, which is basically 150 times 0.2, is a 30. So I know the next term is a 30 in the sequence. Then I test A3. Again, I use the first value, the value of A, 150, and I multiply it with 0.2 to the power of, this time, 3 minus 1, which is 2. And that is 6. Let's do A4. So 150 multiplied with 0.2 to the power of 4 minus 1, which is 3. This is 150 if you want to have an idea of what is this all the way. So this is 0.008 at the moment. So this is 1.2. A5. Let's just write it in here as well. 1.2. A5 is 150 multiplied with 0.2 to the power of 4. Okay, position minus 1, so that's a 4. That's 150 multiplied with 0.0016, and therefore this is 0.24. So these are the first 5 terms of the sequence. Now the next question is, what can we say about the behavior of this geometric progression? What happens in the long term if we keep increasing the number of terms in the sequence? So we started with something rather large, and then we kept decreasing the number. As you can notice, the number in the sequence got smaller and smaller. So what is happening actually, and by the way, the next one, if you're interested, would be 0.048. So it gets even smaller. What we can say, as we have learned previously, is that limit of n going to infinity of this geometric progression is actually 0. It gets smaller and smaller until it is infinitesimally smaller and close to the value of 0. Let's have another example of a GP. So suppose now we start GP at -5 and our common ratio is 4. Write down the first 5 terms of this sequence. So we start at -5. A2 is that -5, the first term, multiplied with ratio which is 4 to the power of position -1. So 2 minus 1 is 1. Therefore my next number is -20. Then A3 is the first term multiplied with ratio to the power of 1 less than the position, so 3 minus 1 to the power of 2. So 4 to the power of 2, 16, times -5, that's -80. A4, that's negative 5, the first term, multiplied with 4 to the power of 4 minus 1, so that's power of 3, and that's minus 320. A5, the last term we have been asked for, is minus 5 multiplied with 4 to the power of 5 minus 1, which is 4. So that's minus 5 multiplied by 4 times 4 times 4 times 4. So that's 256 altogether, and that's gives me let me think, minus 1280, I believe, because we kept multiplying by 4 effectively. So yes, if you multiply 320 by 4, that's what comes out. So your actual sequence starts with those 5 terms: minus 5, minus 20, minus 80, minus 320, then minus 1280. So what can we say about the behavior of this GP? Again, what is the limit as n goes to infinity of an? What is happening with this sequence? Now this time you see that we do not get smaller and smaller values. What we get instead is that we are actually increasing the size of it. Okay, we increase the size of the number that comes out. We keep multiplying by 4, therefore expanding the number. So actually the limit of that function is negative infinity. I know it's negative because we started with a negative term and we kept multiplying by positive ratio. If we start any sequence with a positive number, such as 4, and then the ratio is, let me rewind that, actually the modulo of the ratio is greater than 1, then we always have a divergent sequence, meaning that it will go to either minus or positive infinity. If the modulo of the ratio is actually less than 1, then what happens is that we actually have a limit of 0. That's why on the previous example, when the ratio was 1 over 5 and we changed it to 0.2, the modulo of that ratio was less than 1, therefore we had convergent series, and that was going to 0, to a limit of 0. So that's just a piece of information that you might find interesting. That's how we basically look at the behaviors of GPs without even considering where it starts. There are obviously other combinations. If, for example, the first term of a GP is a fraction itself, what happens if the ratio is less than 1, etc. We can look at that later on as well, if we want to. Now, geometric sequence in Java, so similarly trying to implement GPs into your favorite programming language. We start by defining an array, so we open a new array of 10 positions. So my array, I can just imagine it like this, will have 10 empty spaces. We define a value of a, which is what we called previously a1. Remember, we refer to it with a 0 when it comes to programming and computing applications. So my a1 is 2. My r, the ratio, is 0.5. So I already know, or I should anticipate, that my GP will be converging to a 0, as explained on the previous page. And then we open that for loop. So again, we need only one for loop. We initiate n to be equal to 0. We want to first plug in value of the first term into this position 0. N must go up to the length of my array. So it goes up to 10 in this case, because my array will have 10 positions. Remember though that they are indexed at 0, 1, 2, 3, up to 9. So there is no such thing as a 10, okay, that doesn't exist because it only has 10 positions. So it's perfectly fine for n to go up to, but not including 10. And n goes this time in increments of 1 because I want to fill in every single position. So I keep moving by 1. And then every time I loop this, every time I go around the loop, then I replace the value in that nth position. In the first instance, when n is 0, we are looking at a of 0. to be equal to a0, which is 2.0, multiplied with math.power Rn. Now this is a method from the class math, which basically takes the first number in the bracket and raises it to the power of the second number in the bracket. So effectively we are ending up with Rn. Now you will notice that what we are doing here is taking the first value, multiplied with a ratio to the power of n. Now, not n minus 1 as the previous formula suggested, but this is perfectly fine because of that switch which we did. So we switched indices. We are not starting at 1, we are starting at 0. So testing this, if you imagine n is 0 first time we go through the loop, then we take first value of a0, which is 2 at this point, multiplied with ratio is 0.5 as explained, to the power n, but n in this instance is 0, so to the power of 0, making this whole thing 1, so entire calculation gives back 2, or 2.0 if you want to think about it as a double. So a0 takes a value of 2.0, so you put 2.0 into that position exactly like you want it. You want to start your sequence with 2. And then second time we go through the loop, we increase n by 1, so a of 1 is the next position I'm trying to fill in. So if this is 1, we have a0, which is 2, multiplied with 0.5, okay, again using that method, 0.5 to the power n is 1, like I said, so you have 2 to the power of multiplied with 0.5, and that's a 1, so 1 or 1.0 enters that position, and so on, exactly like you wanted. The only thing you need to keep in mind is that the indices start at 0, not 1, and therefore we are allowed to do it like that. Now, moving on to the series. So series are nothing more than adding up particular sequences. And this is surprisingly important and has massive applications in some high-level methods that I'm not going to mention for obvious reasons. I don't want to scare you off too easily. But if you're interested, following this video, try to dig in a little bit into either Taylor series or Maclaurin series, or if you're really brave, go for Fourier series and Fourier transformations. Some pretty powerful stuff that you can take out from there, provided you understand the concept of series to start with. So here we are just looking at adding up the terms. So if we have a sequence here, for example, this is, by the way, AP. This is or is it? No, it's actually, pardon me, it's not arithmetic progression, because here we added 3, here we added 3, that's fine, but here we have added 4, so immediately it's not arithmetic progression. But nonetheless, we still can take a series over it by adding up its terms. We would need to know a particular rule for that sequence in order to create a series from it. But what we are going to do is again focus on arithmetic and geometric progressions and arithmetic and geometric series, therefore, which come away from that. Now we could be using our favorite sigma notation. So if I want to take the first let's say 5 elements of a sequence A n, okay, if that was my sequence, let's say, I could take n varying from 1, so n takes a value of 1 to begin with, up to value of 5, and therefore that would be a1 plus a2 plus a3 plus a4 plus a5, okay, and then I would need to find these 5 values, add them up. But to keep things simple and to get rid of this sigma notation in the short term, what we are going to use is this notation for summation or for series, which is Sn. So that means I'm taking, in this case, S5, the first 5 terms of the sequence. So that's the sort of notation we do. So if I mean S3, then therefore you need to take A1 plus A2 plus A3 together and add them up. So if that was my sequence and I wanted to create series over it, and I was interested in the first 3 terms, then I would just add 1 plus 4 plus 7 which would give me 12. And that's the result of my series, of taking the series over that sequence, of the first 3 terms of that sequence. Now with arithmetic series, what we are going to do is we are wondering of how can we calculate the Sn, the summation, when n is very, very large. Obviously we need to derive a formula for it, because okay, if I have a particular AP, arithmetic sequence, arithmetic progression, such as 5, 11, 17, 23, okay, I could take S2 or S3 or S4. I have these 4 terms. But imagine if this sequence is going on forever. Maybe it's an infinite sequence, or maybe it terminates at some other stage, maybe at 83 it terminates, and I want to add up all the terms. I don't want to actually calculate every single term and then add them up. It's not very convenient if there is loads of them to calculate. So what I need is a particular formula for Sn if we have AP, and then of course we will derive another formula for GP. So what we do to evaluate this quickly. Now I'm going to briefly introduce Gauss method on a particular case of arithmetic progression, which is natural numbers from 1 to 100, and then we are going to apply it in order to derive the main formula. So what Gauss did was very, very clever way of reversing the sequence. So let's imagine that we are interested, to begin with, for the sum of natural numbers from 1 to 100. So I can write sum of 100, okay, first 100 numbers of a sequence which starts with 1, goes with 2, 3, 4, terminates at 100. This is arithmetic progression because we keep adding 1 to every single term. So S100 is equal to 1 plus 2 plus 3 plus 4 plus yada 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 plus 98 plus 99 plus 100. Okay, I could write it like this if I wanted. Now what Gauss did is said, okay, we know something important about addition of numbers. The important quality of that operation is that we can change the order. Just like we said in previous weeks, the addition is commutative, so that 5 plus 3 is the same as 3 plus 5. Therefore, we can be clever about it and write the sequence the other way around. So I can write 100 plus 99 plus 98 plus 97 plus blah 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 plus 3 plus 2 plus 1, okay, the same numbers just written in different order. And this is surprisingly helpful because now if we wanted to add those series together, so one series added to another series like that, so we add up everything in every column, and basically everything on the left hand side here is being added together. So S100 plus S100 is 2 S's of 100, okay, think about it as being X really. So you have 2x, 2 unknown values that you're trying to find, equal to, well, what does it equal to? If you think about combining them, numbers in this particular order, which you can do because of the commutativity of addition, what's going to happen? 1 plus 100 is 101. 2 plus 99 is 101. 3 plus 98 is again 100 plus 1. And on the other end, you still have 101 every time you add up pair of numbers like that. So you have 101 coming out from every pair of numbers. And how many pairs of numbers you have? Well, you need to imagine you have 100 numbers in a row, don't you? Because you are going from 1 to 100. Therefore, 100 times 101 is being added to itself. So 2s of 100 is equal to 10100, so 10,100. And then algebraically get rid of this 2 by division by 2, so divide by 2 on both sides, and quickly you will see that S100 is actually 5,050. So 5,050 is the result of adding up the first 100 numbers. So simple trick using the quality of addition to enable us to evaluate the sum of the first 100 numbers. It would indeed work with any number of numbers, of natural numbers, as long as they are natural, of course. If you go into real numbers or complex numbers, then you could be in real trouble trying to add them in. Nonetheless, Gauss method is quite useful when we want to derive the main formula for AP. So for arithmetic sequence, we already said that the arithmetic sequence starts with the first term, so A1. So we start with A1, and then the next term of that sequence will be one difference added to A1, wouldn't it? Because A2, remember, is the first term, A1, added to n minus 1, n minus 1, n being that position now, a number of the positions, so n minus 1 is just 1 multiplied with the difference. In this case, A3 is the first term plus 3 minus 1, which is 2 multiplied with the difference, etc. So what I can do, I can write the sequence as A1. After A1 I have A1 again plus 1 difference, and then I will have A1 plus 2 differences, then A1 plus 3 differences, etc. until I reach some last term. So using Gauss method and this sort of thinking, I can write summation of n terms in a sequence, any sequence, it doesn't have to be natural numbers, is A. Okay, I will use A instead of A1, just to make sure we don't mess up, misinterpreting comma with a 1. So I have A, first term, plus second term, which is in fact A plus the difference, plus the third term, which is in fact A plus 2 differences, plus the fourth term, which is the first term plus 3 differences, plus dot dot dot. I will end up with some last element if our sequence is finite, and let's just say straight away that we are looking for the summation of finite sequence. Okay, so finite series that we evaluate there. I will have L at some point. That will be the last term. Let's denote it for now like that. I will have L minus the difference. Okay, so one difference away. Remember, to this term, to get the next one, I need to add the difference. So that's why it's L minus D, so that these two basically cancel out to give me L. And one previously would be L minus 2 differences. 2 differences away from the last term. Now, Gauss method being applied, I can write the same series the other way around. So I can write L here plus L minus D plus L minus 2D, and you should be able to see what is happening right now and how this will nicely cancel out the differences. But here we have technically 3 differences away from the last, plus blah blah blah, plus here on the other end, if we switched it around, we would have A plus 2D and then plus A added to D and plus A. Okay, using the same principle like we did before, we are trying to add 2 series together to find out something important there. So we are adding 2 sequences together. If you pair it up like we did before, A will be added to L, then A plus D will be added to L minus D, but positive D with minus D will cancel out. So again, you end up with A plus L on its own. Okay, so let's just write it out. So that's 2 summations of n is equal to that, plus again here 2D positive minus 2D, they cancel out, so you end up with again A plus L, again A plus L, and then plus blah 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 plus again a plus l. I'm not going to write all of them, but basically it's plus a plus l added in so many times. How many times? Well, n times. N times because we have n terms in this sequence. In other words, two summations of n is equal to a plus l, first term, plus the last term, multiplied with the number of terms. Okay, and then what you can do, you can bring this 2 to the other side, so you will realize that Sn is equal to a plus l multiplied with n over 2. Okay, that's the summation, except that very often we know where we are starting the sequence from, but we don't know what is the value once we terminate. Therefore, what else we can use to expand this formula and therefore derive the proper formula I want you to be able to know and use is to realize that L is actually first term, okay, plus n minus 1 multiplied with d. Okay, so that's just realizing that last term is that nth term that we would be looking at this stage. So if you replace L with that formula into the formula for the series, you will derive the main formula for a series of AP of arithmetic progressions to be Sn is equal to n of 2a plus n minus 1 multiplied with d over 2. Okay, it is like that because if you substitute it in, you will have a plus a, meaning it's 2a plus n minus 1d comes in over 2. This formula, by the way, you don't need to remember. It's going to be given in the appendix, but you just need to be aware of how it came about, why it looks like it does, and how we can apply it to some problems. Okay, so that formula I had it written here, actually printed, but I annoyingly run over it a little bit, so let me just erase it so you can see it printed out nicely. And this is what we are going to be using in the next few exercises there. So find the sum of the first 40 terms in the series 5 plus 8 plus 11. I want to apply that formula which I just derived. Now, what I know from the information I have been given, even though it might look like not much has been said, actually, I know that n is 40. I will be looking to find S40, okay, sum of the first 40 terms, in the series 5 plus 8 plus 11. From this, I can deduce that the first term in the sequence is 5, so that's where I start from, so I know the value of A, I know the value of n. What's the value of D? Well, what number I need to add from 5 to get to 8, what number I add to 8 to get 11? The answer is 3, so I know that the difference is 3. Plug it into the formula, so that will be 40 multiplied with 2 times 5 plus n minus 1, so n minus 1, n being 40, I can write immediately 39 multiplied with difference of 3 over 2. So now I can simplify here, 40 and 2 can go away, so I will have 20 multiplied with 10 plus what's the actual value of this? I think it's 117. Yep, 117, so I will have 20 multiplied with 127, and therefore my solution is, or the answer is 2540. Okay, that's the series or the sum of the first 40 terms in this particular sequence. Okay, so if I wanted to evaluate it without a formula, then it would probably take me longer than this entire video, because I would have to create the 40 terms and then add them up one by one. The formula simplifies everything for us. Here we have the implementation in Java, very similar to what we had previously, but now we are also summing over the terms and then and then we evaluate the series. So we start by defining an array of this time 100 items. I want to create a series over 100 terms. We initiate A0, the first term in the sequence, which will be 2. The common difference will be 1.5. Okay, even though I used natural numbers to be differences, or well, for ratios we did use rational numbers, but for differences I can use whatever number I want, so that's fine. 1.5 will be the difference. I start by saying sum1 and sum will be variables holding a 0 to begin with, just to initiate them, and I will actually evaluate the series in two different ways. So two different ways which are two different approaches you can take to evaluate the same thing. So here, using for loop, I can initiate counter 0 n going up to the length of the array, as explained before. So this time n will take value up to 99, n goes in increments of 1. Then I can replace the value at position n with the initial value plus n multiplied with d. So this is equivalent to our mathematical notation that we had, which was the first term plus n minus 1 over d. And again, the only difference is that we have n, not n minus 1, again because of that shift from index 0 up to 1, or the other way around rather, when we look at programming. So that's why it looks like n multiplied with the difference being added to the initial term 2. And then we calculate summation, so we simply add to what summation previously held plus the newly found term, the newly found value in the position. And then we loop it so many times that the sum is created. Okay, and that creates the series. Now, second approach, so that was approach number 1. Approach number 2 here is to actually initiate n to be the length of the array. Okay, and then what we do is we apply the formula which we had on the previous slide. This is exactly the same as we said before. Sn is equal to n multiplied with 2 a's, 2 times the initial value, plus n minus 1 times d over 2, divided all together by 2. Keep in mind the brackets that need to be there. All of it is divided by 2. So we just apply the formula, and then just to check, we have one line of code here to print sum, so what comes out from the first method, plus sum1, which is coming out, the number coming out from the second approach, and then the difference between the two. If you run this code, they both should give you the same value, and therefore the difference should be 0. They are equally the same. So two different approaches. The first one has an upper hand, I would say, only because you are actually storing the initial values, or you're storing the terms in the sequence, so maybe you can later on access individual values from there. With the second method, you simply use the formula, so the terms in the sequence do not exist. They are not held in the memory anywhere. Having derived the series equation for arithmetic progressions, now it makes sense to do the same for the other type of sequences we have studied so far, which is geometric progressions. Remember, with geometric progressions, to go from one term to the other, we multiply by some common ratio. So we keep multiplying by the same number over and over again as we move on. Now, to get the nth position value, we had the formula that we take the initial value, the very first one in the sequence, and multiply it with r to the power of n minus 1, so 1 less than the position we are looking at. If we are trying to add them up, meaning we create a series over geometric sequence, then we need to add the first item, the initial one, which by definition is a, to the next one. The next value will be, well, initial value multiplied with a ratio, okay, just because of the nature of geometric progressions, times another ratio. The next term is ar squared. The next term after that times another ratio is ar cubed, and so on. It goes on until it terminates eventually with ar n minus 1, okay, with that term, with the nth term. But what about n minus 1 term? Imagine plugging in n minus 1 in here, you would have n minus 1 minus 1. So overall, you would have AR n minus 2. So playing around with indices enables us to actually write down the entire sequence, even though I don't know what n is. Now, I could be applying Gauss method to find something interesting or something that helps me develop a formula for it, but actually Gauss method is pretty much useless in this case. Gauss method was good for arithmetic progressions because the differences were common, so we kept adding up a common difference to every previous term. However, here we have multiplication, so that approach would no longer be as helpful as it was before. But what I can do, I can cleverly decide to multiply both sides of this equation with r, with ratio. So if I multiply Sn with r, I will have ratio times Sn. Okay, on the right hand side, however, I will need to multiply ratio with every single term, similarly to what we do if we have a number in front of some brackets. This 2 must multiply x and also must multiply y. So if I multiply everything here by r, r will multiply with a, so it gives me AR. Then AR will multiply with r, so that will be AR squared. Then AR squared multiplied with r is AR cubed, etc. So on. And then at the other end, AR n to the power of n minus 2 times another r is actually AR to the power of n minus 1, and the last term becomes AR to the power of n, just applying the laws of indices discussed earlier in the module. Now, why this is helpful is because now I can do Sn minus Rsn, which means I have to take away the second line from the first. So A will definitely remain after I do that. However, the majority, almost all the terms will cancel out because you will end up having AR squared minus AR squared and AR cubed minus AR cubed, and even at the other end you will have AR to the power of n minus 1 minus AR to the power of n minus 1. So all of them will cancel out, all of them will have a pair inside, apart from the very last term and the very first one. So taking the first line minus the other on the right hand side gives you a minus AR to the power of n. And this helps us develop the actual formula, because now what we can do, we can take common factors out. On the left hand side you can notice Sn appears in both terms, so I can take it outside of the bracket, factorize it this way, so I will have 1 minus r inside of the bracket. On the other hand, I will have a 1 minus r to the power of n, and then the very last step is to bring that entire bracket into the other side by dividing through by it. So if you divide through by it, you will end up with the actual formula for the series of geometric progressions, which you can see here right on the screen. So to get the series over so many elements of a geometric progression, you need to know the first element and then multiply it with 1 minus ratio to the power of the number of terms that you have, and at the bottom 1 minus ratio will be the determinant. Now the only condition is that r cannot be 1, because if r is exactly 1, if ratio is 1, then well, we cannot do this summation whatsoever, because we end up dividing by 0, which is of course impossible to do. But actually at the same time, think about a sequence which has a ratio of 1 and it's a geometric progression. Well, in such sequence we start with initial term, let's just say we start with a 4, and then the next term is found by multiplying the initial value by 1, so that gives me 4 again, times 1 it's 4 again, and then times 1 it's 4. Basically what I'm saying in there is that you will end up with a sequence of exactly the same number n times, however many times you are asked to repeat it. So in this case To get the series over that sort of sequence, which is geometric as well, you don't really need any sophisticated formula. You simply multiply 4 by n, as your common sense would suggest. So as long as ratio is not 1, you apply the formula. If ratio is 1, well, then all you need to do is to multiply a particular initial value with the number of terms inside of the sequence. Let's have a look at an example now, just so we can apply the formula that we just derived. Find the sum of the first 20 terms of the geometric series 2 minus 8 plus 32 minus 28, and so on. Straight away you will notice that we are swapping between negative and positive numbers, so I expect my ratio to be negative. Nonetheless, ratio is something I need to calculate first and foremost. So ratio, remember, can be found by taking any term inside of the sequence and dividing it by the previous one. So I can take negative 1, 2, 8 and divide it by 32. I could also take 32 divided by previous one, which is 8. I could also take negative 8. Oh, pardon me, that was negative 8, of course. Or I could take negative 8 by 2. In all of these cases, I would find that ratio is common, is the same, and it's exactly minus 4. I also know by looking at the sequence that A, the very first item, is 2, and what else? I have been given value of n, which is 20. I want the sum of the first 20 terms of the geometric progression. So now it's all about application of the formula. So Sn is equal to A has a value of 2, times 1 minus ratio, but ratio we can already plug in minus 4 into that space, to the power of n, so power of n, power of 20, over 1 minus the ratio, minus 4. And then it's all about calculator's work, because it will be hard to actually evaluate 4 to the power of 20 otherwise. It would take way too much time, so just turn on your calculator and we will shortly see that the answer is negative 439,804,651,110 according to my calculator. Some calculators can actually give you this result written in that format, so don't be surprised. It can say minus 4.398 multiplied with 10 to the power 11, I believe, because when you try to move this decimal point by 11 places to the right, you unwrap the entire number, or at least this is an approximation that some calculators give when computing large numbers. Or it could say actually multiplied with e to the power of 11, but really it's implied that 10 is being raised to the power of 11, and that's the number. So just be aware of something like this. This sort of formatting can happen if you deal with large numbers. Anyhow, here we have number in billions. So 439 billion something something something. The next step really of the analysis is to think about what is happening with the series as we keep progressing. So the next term you can imagine of the sequence would be very large and positive. So if we added that very large positive term, we would probably have a positive value of the series, which would be even bigger than that in magnitude. But that's for later. This is just to make you think about how sequences and series evolve and how they behave long term when we have n tending to infinity. Now, talking about infinity, let's just do one more thing with geometric progressions, which is getting the formula for the series to infinity. Now, our series formula was Sn equal to A multiplied with 1 minus r to the power n over 1 minus r. That was our formula, but now what is happening in certain situations if the modulo of the ratio is less than 1? Meaning that if the ratio is between minus 1 and 1, and that means in pure English that the ratio is a fraction, or a 0, then what is happening really in long term, as n goes to infinity, this little term r to the power of n, this r to the power of n is actually going to 0. What I'm trying to say here is that if you have a ratio which is a fraction, let's pick our favorite fraction 0.5, and you raise it to some large power, then basically that term becomes insignificant, and we can't just say it goes away, it's a 0. We can notice that by applying small powers, because 0.5 to the power of 1 is just 0.5, but if you raise it to the power of 2, for example, it's already half of half, which is 0.25, it's a quarter now. 0.5 to the power of 3, well, it gets even smaller because that's 0.125. The next one would be 0.0625, and so on. So it only grows smaller and smaller until, as it approaches infinity, it becomes insignificant, which means that the formula for series over infinite amount of terms is a on its own. Since this goes away, you only have a multiplied with 1, giving you a over 1 minus r, 1 less than the ratio. So this is an extra formula that we have, but in terms of remembering, we don't really need to do that because we can just deduce it from the main series formula for GP. Now, we can apply this formula for infinite series to solve this sort of a question. We are told that sum to infinity is 500, so we know if we sum over infinite amount of terms, we are going to have 500 to be the total value, and we know that the first term is 5, so we know a is 5, and then it's a simple case of substituting this into the formula. So on the left hand side, sum to infinity is 500, on the right hand side you have a, and that's a 5, over 1 minus the ratio, which in practice means that we can bring this 1 minus the ratio to the other side and write 500 multiplied with 1 minus ratio is 5. What we can do next now is bring this 500 to the other side by dividing through by 500. So 1 minus r stays on the left. On the right you have 5 divided by this 500. In other words, 1 minus the ratio is 1 over 100. Okay, I simplified this fraction by dividing by 5, and then rearrange all of this to find that r is equal to 1 minus 1 over 100, and therefore r, the ratio, is 0.99. That was our ratio. If we start with value 5 and we have this ratio and we sum over infinite amount of terms, the total of those terms will be 500. So we use the formula just to find something out about the progression, how it progresses from term to term. Now, we had Java codes for all the previous calculations, so it makes sense to actually have one here. Again, the approach is similar to the one we had for arithmetic progressions, for series of arithmetic progressions, shall I say, in which case we open up a new array of 100 empty slots, and then we fill them in with the terms of the sequence. And then a0, the very first value, is 1, ratio is 1.5. We initiate two other variables which at the moment will hold value of 0. We will eventually replace them with the value of the series. We have two approaches again. So this is approach number 1, this is approach number 2. The first one uses iteration with n starting at a 0 because I want to have a of 0 entry. This is what we call the first entry, the initial one, which has index of 0. Then n goes up to the length of the array, so up to 100 in this case, meaning that the last one will be a99. And then n goes up by 1 every time we loop it. A n value, so the value in the nth position, is found by taking the first value, a0, which we said will be 1, multiplied with math.pow of Rn. So again, we are using method pow on the class math, and what it does, just let me remind you, is taking the first argument inside of the brackets and raise it to the power of the second argument inside of the bracket. So in other words, what we are doing here is we are doing an is equal to a multiplied with r to the power of n. Now, mathematically, we had the formula r to the power of n minus 1, but here we start counting and identifying indices with 0, not with 1. So we have this shift between 0 and 1. We start counting at a 0. Therefore, we no longer need this minus 1 inside of the formula. So here in that line, for any n, we are basically calculating the value of that term and then placing it inside of the array. And then in the second line, we update the value of sum by the newly found value that just entered my array. And by doing that, by looping so many times, in fact 100 times for an array of size 100, you fill in the entire array, and at the same time you calculate the summation. You calculate the series over that sequence, which is the total of all the terms. So that's the robust method, the very brute force method, if I can call it like that, but it gives you the right result. It involves 100 iterations though. The second method is to use the formula which we just derived. So again, we have a multiplied with 1 minus r to the power of n all over, so all divided, bear in mind all these brackets, all divided by 1 minus r, which was precisely the formula we last derived. So that calculates sum 1, and at the end, once again, we print the sum, we print sum 1, and the difference between sum and sum 1. If everything went well, then the difference between the two should be 0. Whether you use iterations, actually calculate all the values and then add them up, or whether you use the formula, you still are going to get the same end product. The end result will be the same. Now, for the final thing in the video and in this topic overall, we need to talk a little bit about the recurrence relation or recursion. Everything we have done so far and everything you probably have done in object-oriented programming thus far was based on iterations. We had for loops, and then we iterated with the index always changing. So we had this for statement. So for example, for n equal to 0 to begin with, n less than some certain value, I don't know, maybe 5, going in increments of 1, we had some sort of calculation based on that, based on this counter. In terms of our sequences, again, we had formulas for arithmetic progression, for example, for the nth term to be a plus n minus 1d. Again, what was changing all the time once we know initial value and the difference was that counter, was that specific index or position or place within the sequence. With recursion, what we are doing instead is we are looking behind us. We are looking at the previous case. So once we know the initial term, the initial case, which we call the base argument, then we can sort of find out everything else about our relation based on that. Just to give you a short example, I could have a sequence described recursively in the following way. I could have a base case, the base value to be, let's say, 3, and then an is described by taking twice an minus 1, so twice the previous term. In which case, if I wanted to calculate let's say 4 for simplicity, then what we would do, and what your program would do if you were actually programming recursively, which is an option by the way, you could look at 2 times a3, which is the previous value, the previous position before 4, and then you would realize, hang on a minute, I don't have a value for a3, so actually I need to take 2 multiplied with 2 times A2, okay, because A3 can be found using this formula by taking 2 times A2. But hang on a minute again, I don't have the value of A2, so now it's actually 2 multiplied with 2 multiplied with 2 A1s. And now I do have A1, it's available to me, I know the base case, so now I can calculate the rest. So I can have 2 multiplied with 2 multiplied with 2 multiplied with 3, and then sort of fold it on together to have the actual value of A4. So that would be 6, so I would have 2 times 2 times 6, and therefore I would have 2 times 12, and that's 24. So I would find the value that I'm interested in by recursively referring to the same rule until I hit the base case, at which point I just fold everything together and find what I was initially looking for. Now, in terms of programming, some functions, some programs are going to be more efficient if you use recursion over iteration. In some cases, actually, it wouldn't be possible to define your program or to define a function without the use of recursion. In most cases, recursion looks a bit nicer, a bit neater on a page rather than iteration. It's much easier to follow. We will see one short example of the difference between iteration and recursion in terms of a program to find a factorial right towards the end of this video. But for recursion to happen or to take place, we need to ensure that two sort of qualities or two things are satisfied. So first of all, we need to ensure we have some base values. So they must exist. So whether it's just A1 that you are referring to, or maybe A2 as well, or maybe even A3, you have to have some base cases, okay, for which the function does not refer to itself. So we have some sort of a basis to start our calculation from. And then second quality is that every time relation does refer to itself, we are getting closer to the base value, just like I did with my example just half a minute ago. Okay, so when I was getting closer to that base value A1, which I knew. Now, Fibonacci sequence is the most common sequence which is recursive. It's recursive because the very first value in that sequence, A1, as you can see, is 1, and A2 is 1. This provides the base case of Fibonacci numbers, and then any other number is simply found out by taking the previous value plus the another value which was before. So the previous two values essentially are being added together to get the next one. So that 1 plus 1 is 2, and 1 plus 2 is 3, and 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, and so on, indefinitely. It's not an arithmetic progression, it's not geometric progression. So it's not very useful to apply any of the formulas that we derived today. It will be difficult to find a Fibonacci number inside of a sequence without using the recursion. We would have to do that. So here we have the Fibonacci numbers written with f of n rather than a of n, but the principle is the same. So we have a base case defined, as I did really, and we have the general formula for it as well. Do have a look at Fibonacci numbers. It's a very peculiar kind of mathematics which hopefully gets you interested. On the slides you will have a link to a video which I recommend you to watch. Hopefully it will intrigue you a little bit and ignite an interest in numerology or well, patterns really, because that's essentially what we are looking at, some patterns which appear in many places in nature and around the world. Now let's have an example of comparing iteration to the recursion. So we take a simple arithmetic progression which is 5, 7, 9, 11, 13. So they are odd numbers starting at 5, If we wanted to write the formula for the sequence, we could do that both in using iteration and recursion. If you look at the iteration, you will find that we apply familiar formula to find the nth term, and if we want to tailor it specifically to this sequence, we would just plug in 5 into this place, and 2 was the difference, so 2 into that place, rearrange, and you would find the actual specific formula is 2n plus 3. But every time we move through the sequence, we add one more common difference, which we can see here that, for example, to get a5, we add 4 common differences to the initial value, etc. With recursion, it's much nicer to actually show you how it works, because all you do is you define the base case, the base argument, which is 5, and then you just add 2 to the previous one, and then you add 2, the common difference, to the previous one, to a2, and so on. So the actual formula is this. It's looking at the previous value, index minus 1, plus the common difference that we keep adding on. And therefore, specific formula for that sequence is it's not great. All we did really was just put 2 instead of d, and we still look at the previous value. But it's much neater and easier to find the next value in that sequence, the next term, using recursion rather than iteration. But generally speaking, you always have an option. You tend to always have an option in terms of maths anyway. As long as you know the initial case, the base case, and the common difference or common ratio, if you're looking at geometric progressions, then it's your choice, your call, if you're doing it iteratively or recursively, if you're finding an in either of the methods. Recursion in Java, well, looking at the Fibonacci numbers here, what we can do to implement them into a Java program is to actually initiate array again, in which we are going to plug in 100 Fibonacci numbers. We initiate F0 and F1, so immediately we say what is in the first 2 positions inside of the array. These are our base case values. We have the for loop here, which means that this is not really a recursive program. It just applies the recursive idea, but it's still an iteration. We still vary n. Okay, so it's still iterative program, iterative piece of code. In which case we look at f of n, f of 2 at the first instance, to be f of 1 plus f of 0, basically. So 1 plus 1, which will give me 2. And then the next time we go through the loop, n takes a value of 3, so we take f of 2 plus f of 1, so those two are added together to give me 3, and so on. We get the Fibonacci sequence that way. And then for any value inside of the array, so for any value here, we just print it out. So we print all 100 Fibonacci numbers onto the screen. Now, last thing with recursion versus iteration, to reiterate the point, in iteration you have some general term of a sequence, and we apply the formula over an index. So we have index which varies, okay? So index goes on and on, and we keep changing that in terms of the position there. So usually it's a set of natural numbers. It could be other sets of numbers, but let's just stick in this module at least to set of natural numbers. Then recursion is when you have available a general term in terms of the general term in the previous steps, based on some base value, so base term. The very first one, for example, a1 or a1 and a2, like was the case with Fibonacci numbers. Now, there is one more video I would like you to watch. It's 7 minutes, but it's great in terms of what it does. So it introduces 2 programs, both to do the same action, to actually calculate the factorial of particular number. But the person who did the video, by the way, it wasn't me, have written the program iteratively and then recursively. So you can start noticing the differences that there are in terms of how the numbers are achieved. That person who did the video actually goes over and writes step by step how the device or computer is actually evaluating the factorial in both ways. So it's well worth to watch it. But the bottom line is that here we vary some counter, some index, okay, which is I in this case instead of n. But here in recursion, what we do, we just call upon the same function, so the same function which was defined. By the way, these two are written in Python language. However, the only difference between Java and Python is the pure syntax. So what you would put at the end of any line, how would you sort of define how I varies, how the index varies here. In Python it's much easier with the range function there. But the bottom line is that you should be able to understand it, especially with somebody explaining this to you line by line. So don't be put off by the syntax. Don't be put off that by the fact that it looks different to your usual Java. Further reading for this week is chapter 19 of the Mathematics for Engineers. I recommend you look into that ebook for any further practice, for exercises, to have a bit more of an idea of the arithmetic and geometric progressions. So remember, let me know if anything on the seminar activities or anything inside of this topic or well, module overall doesn't make sense, or anything that you need to go over. You will find my email address on the Moodle page as always. So thank you for listening, and I hope to catch you in the next video. Thank you.